You know about the deferred update replication technique, which was designed actually independently from the things I presented before in the context of database replication. So it's a pretty mature technique. There are many implementations of this idea. Some of them with some variations, and there are even open source implementations of this. And you're going to see that it's very similar to the multi-primary passive replication. Okay, so the idea of the multi-primary passive replication was to actually make the bridge between object replication and database replication. So again, let me show you this technique using this framework that I had before. The client submits a request to a server, right? So you can choose one of the servers. There is no phase 2, there's no server coordination. And this server, it executes the request, right? And then it goes through some agreement coordination. If everything is alright, the changes are accepted and the response is sent back to the client. This is, if you think of multi-primary passive replication, it's pretty similar for update requests. The client can choose one of the servers which is going to execute the command, then there is an agreement, and then a response to the client. So the model is the same model as for multi-primary passive replication. But the thing is, we are here now in the transactional model, remember? It's not the object model anymore. So transactional model means that the client may submit a sequence of requests that are part of a same transaction. Not every request is a transaction. So what happens here is that in my framework, in my generic framework, I may iterate through some of these phases. So for each request, the client chooses the server, it sends to the same server its request, receives a response, and then it can do this for any number of requests. Eventually, the client submits a commit request. And when the client submits the commit request, is that you reach actually the termination of the protocol, and then you have the agreement phase. So inside this cloud here, which I'm going to detail in the next slides, there is a communication protocol, and there is also some certification and the final decision whether to commit or to abort the transaction. Okay. So the deferred update replication, it distinguishes between read-only and update transactions. So in any case, all the transactions, they are submitted to only one server. So it means that if it's a read-only transaction, the requests are all reads. If it's an update transaction, you can have a mix of reads and writes. Now the difference is, at commit time, if the transaction is read-only, then it can be committed immediately without any communication among the servers. But if it's an update transaction, then it should be propagated to the other replicas for certification. Certification is what we called before checking whether two states are compatible. So this has a specific name in the context of database, and it's called a certification. And if the transaction passes certification, then it is committed. This protocol here, it's for serializability, right? It's not for linearizability anymore. So if you look at the read-only transactions, you're going to see that you can have two clients choosing different servers and executing their transactions, right? A sequence of read requests, because it's read-only transactions. And once the commit is requested, the transaction finishes, right? There is no communication among the servers for read-only transactions. This is different from everything I told you before, right? Even in multi-primary passive replication, read-only operations have to be broadcast. Now, read-only operations, they are completely local. So why can I do it here? I could not do it before. Yes, because I changed my consistency criterion. Now I'm talking about serializability. Serializability allows us to do local read transactions, right? Linearizability does not allow us to do that. In fact, it's a non-bound on algorithms for linearizability. You must synchronize the reads as well. So for For updates, you submit your reads and writes. Eventually there's a commit, and then you have our cloud where there's a synchronization among the servers. Notice that I could have, so here I also have an update transaction, but I could have a read-only transaction here that does not even see other update transactions. Okay, so let me tell you what's inside this cloud, and maybe not so surprisingly, I'm going to start by placing an atomic broadcast inside the cloud. So this is very similar to multi-primary passive replication. I require a deterministic certification test. I must be able to tell deterministically whether transactions passed certification test or not. And well, it turns out that I could also place inside my cloud an atomic commitment abstraction, which is maybe familiar to some of you. It's certainly something that belongs to the area of databases. But an atomic broadcast results in fewer aborts. I'm not going to go into detail about this. So let's place an atomic broadcast inside the cloud. Now I can think of my transactions as going through a sequence of states, right? So when the transaction starts the execution, it is at some server S. So transaction T starts the execution at some server S. It is in the executing state, and then the clients are submitting reads and writes. Once the client requests the commit of the transaction, it goes into the committing state at this server. And from the committing state, it can go to two states, which are final. It's either committed or aborted. Okay. So let's have a look at at one execution to try to understand how this deferred update replication works. So I have my client. Client 1 chose server 1 to execute the transaction and submitted the write operation. And to keep things simpler, there's only one operation in this transaction here. And then later the client submits a commit operation. So until now, my transaction T is in state executing at server S1. Then it is atomically broadcast, right? And it's going to be delivered by all the servers. So whenever the transaction is delivered, so it passes to the committing state at each one of the servers. Now, the executing phase only happens at one server because it's only executed at one server. But the committing phase happens at all servers because it's going to be delivered by all of them. And inside the committing phase, I have my certification. So the certification is to check whether what was changed by this transaction here, right, is still compatible with the current state of the server. Very similarly to multi-primary passive replication. And each server is going to do the certification test. In reality, because it depends, so the certification test only depends on transactions that have been previously delivered, right? So they can all do the certification test, which is going to be deterministic, and they are going to reach the same outcome, either commit or abort. And this is what I call a transaction termination. So this is the easy case. There is only one transaction. Let's add two transactions here and let's see what happens. So, so the clients, they chose different servers. They request the commit of the transactions T1 and T2, which are broadcast. Let's assume that this transaction here gets delivered before. Right? Transaction T1 is delivered before transaction T2. So whenever it is delivered, it enters the committing state at the servers. Right? Note that I drew the boxes of different sizes to emphasize that the servers, they may be running at different speeds. It doesn't matter. What matters is the order in which they receive the messages. So the first transaction is delivered T1, and this transaction here, I'm assuming that it is it passes certification and it's committed. Now eventually the second transaction is going to be delivered, and then we are going to run the certification test to see whether this transaction here can actually be committed. Meaning, if it has not read some state that changed in the meantime. Because the transaction executed during a time when the changes made by T1 were not reflected in the database. So maybe if this transaction here depends on some information that was changed by the database, I cannot commit it anymore. Right? And that's what certification does, basically. So it turns out that I can capture my certification test using a very simple expression. So any transaction T, right? For any transaction T, any server S, so the transaction T passes from the committing state into the committed state if two things happen. So we want two things happen. So for all transactions T prime that have already committed at the server, right? Either T prime precedes T. So the notion of precedes means that T prime was committed at the time when T was executed. Right? That's what precedes means. This basically means that if T reads some state that T prime changed, it's going to see the change because T prime was committed already, had finished by the time that T was executed. Right? Or maybe T prime did not finish when T executed, but T prime didn't make any change. So WS means the data items that were changed by transaction T prime, and RS means the data items that were read by transaction T. So T prime maybe did not finish when T started executing, which basically means that maybe T read some data items during the time that T prime was still being committed, so it didn't have a chance to see the values. But it turns out that T prime did not change anything that T read. So they're independent, right? T prime is not changing anything that could violate the correctness of T. So if one of these things happens, then I can commit my transaction T. So that's what the certification does. It turns out that this is very similar to the previous test. I didn't show it like this. Yes?
Certification on one server.
Yes, it's possible. So you can. There are approaches that have the certification executed on one server only, right? It turns out that it's possible, but yeah, no, it's could be done. Actually, we have a prototype that does that. So, as I said before, right, what this means is that if T prime precedes T, then any change made by T prime, they could be seen by T. They could be read by transaction T. Or, this is not true, but T prime doesn't change any items that T reads. So, I can commit T despite T prime. So, let me show you an example. Okay, very simple. I have two transactions. Transaction T reads X and writes Y. And transaction T prime reads Y and writes X. Okay? And let's assume that they are concurrent. They execute at different servers, and neither T precedes T prime nor T prime precedes T. And they execute in different servers. Right? So you can see already here that if they execute on different servers and one does not precede the other, I cannot both commit them. Right? That's the example. In fact, that's the example that we saw yesterday of an execution that is not serializable. So what's going to happen is these two transactions here, they are going to be broadcast to all servers, and they're going to be delivered in the same order. So what it means is that all servers are going to certify the transactions T and T prime in the same order, or also said validate. Now let's assume that that servers validate T before T prime. I could also do the other way around, but as an example, let's assume T before T prime. So T is the first transaction. It's delivered, right? So there is no other transaction. So it certainly passes certification. Now, what about T prime? When T prime is delivered, so will T prime be committed or aborted? Aborted. So T prime, it turns out that T prime, it reads Y, right? And there's another transaction that does not precede T prime that writes the value of Y. So I have to abort the second transaction. So one transaction passes, the other one aborts. Oops. So is it fine so far? So what if I had delivered okay, now let's look at another example, right? Let's assume that now let me change the operations performed by T and T prime. Now T, it reads X and writes Y, and T prime, it reads Y and writes Z, a different variable, okay? And let's assume here, case A, T is delivered and certified before T prime. So T is the first one, it passes certification, right? Now, does T prime pass certification? Still not, right? Because T prime now reads Y, which was written by T. So T passes certification, but T prime doesn't. So the read set of T prime, it intersects the write set of T. So there's one element here, then abort. But let's assume that by some chance, right, T prime was delivered before T. It can happen. Concurrent. So what happens if T prime is delivered before T? So the first transaction, T prime, passes. Would T pass the certification test? Yes. So what this shows actually is that depending on how these transactions are delivered, right, I may have more transactions committing or fewer transactions committing. So if a transaction is aborted, it has to be re-executed, right? We assume that the client really wants to commit to the transaction, so it has to re-execute it. But the performance of the certification test, or the number of transactions that pass the certification test, depends on the order in which these transactions are delivered. Well, it turns out that atomic broadcast, it specifies some order that depends on the implementation details of atomic broadcast. It doesn't depend on the contents of the transactions. Atomic broadcast doesn't know anything about the database, just knows that it has to order transactions. But it happens that depending on how these transactions are ordered, you can have more or less aborts. So this observation here, it leads to an improvement of the technique that is called reordering. So reordering is based on the assumption that order matters, right? And exploits this order. Let me show you how. So in the case before, if I don't have reordering, so my order is going to be given by atomic broadcast, so I can have T1 followed by T2. One transaction is going to abort, T1 is going to commit, T2 is going to abort. Now with reordering, I can check to see whether by reordering the transactions I can have more commits as opposed to the order given by atomic broadcast. Let me show you this example here. So that's more or less how it's implemented. So now each database, it keeps what's called a reorder list. So this is a sequence of committed transactions, right? This list can be as large as you want. It can be the whole database, all transactions executed so far. But in practice, it's not very realistic to keep out the database. So what you want to keep is a short window of transactions, right? And when you deliver, this is a new transaction. It was executed in some site, it was delivered, and now you have to run certification for this transaction T. So what certification does, in fact, is it tries to place T after the transactions that have been committed already. And that's why we run the certification test. I check to see whether T can go in here by verifying whether all transactions that were concurrent to T, let's assume that all transactions inside the box, they were concurrent, executed with T. If none of these transactions updated some data item that was read by T, right? That's how it was. Our test was performed so far. Do you agree? We test whether T did not read anything that was changed by these transactions. Okay, but we saw that this sometimes is not a good idea because I may have to abort a transaction, even though if I could insert it in other places, it will be committed, right? So the idea of reorder is quite simple. If I cannot place my transaction at the very end of my list, I try to find a location inside this list where I can place it. Right? For example, if the reason why, if T has read data item X and T3 updated X, I'd have to abort T, right? But maybe I can place it before T3 because neither T1 nor T2 changed the value of X. So I can try to find a more favorable order to commit this transaction. So my certification test gets more complicated, but I can commit hopefully more transactions. Now, I have to be careful the way I do this, because transactions T3 and T4, they have been committed already. So if these transactions here depend on anything that this transaction changes, then they're going to be invalid, right? And I cannot uncommit some transaction that was committed. There's no going back. Once the transaction is committed, the user has been notified, and they cannot change the state. So what I can do instead is I can check whether T changes anything that T3 and T4 read. If it does not change anything that T3 and T4 read, then I can place the transaction here. That's basically what's done by the second part of my certification test. So the certification test now checks whether the transactions that precede T do not change what T reads, and the transactions that succeed T do not read what T changes. And if this is true, then I can commit my transaction T. So that's the idea. So the ordering certification gets a little bit more complicated because this thing actually captures the notion that I told you before. I'm not going to go through this expression, but what it says is that I have to check for according to the position. I have to verify whether the transactions that succeed my committing transaction, they do not or they do not read what the committing transaction has written, and the committing transaction has not read anything that the preceding transactions have updated. Okay. Now, you can exploit this even further, right? You can go and then realize that T cannot go in here. Why? Because it read something that these transactions here wrote. And then you can do the reorder. You can try the next position. You can try to place it in here. Because maybe, hopefully, the transaction that makes T abort is T4. If the transaction that makes T abort is T4, I may try to place it before T4. But maybe I can't do that either. And then I try one more position, and it still doesn't go, and so on. And then I exhaust my list here, and none of these positions allows me to commit T. Does it mean that I must abort T? That's what the reordering is going to do it, right? But it could do even better than that. I could try to actually reorder the transactions that have been committed already, and then in doing that, I would find a location for T, right? Instead of just skipping. So what's the problem with this? So do you understand the technique? Instead of just trying to find the position in this order, I also reorder the transactions that are in this. So what's the fundamental problem here? Excuse me?
How to reorder?
So and what does it? What's the implication? Yes, so my complexity here explodes, right? This becomes a combinatorial problem. I have to check out combinations and see where I can place my transaction. Before, it was linear with the size of my reorder list. Now it becomes actually exponential of the size. So I have to check out the combinations. So if you think of a database system which was designed for very high throughput, right? Many transactions committing at a time. This is an expensive operation because it has to be run for each committing transaction. So chances are that what I'm going to gain by doing this largely outweighs what I'm going to lose by making the check. So when it's better, just abort the transaction, the user submits it again, and in the meantime, I can commit lots of other transactions. So it may not be such a good idea from complexity point of view. Okay, let me now show you that atomic broadcast, in reality, it's not needed to implement the deferred update technique. And I'm going to replace the atomic broadcast by another ordering property, another ordering mechanism, which is weaker. So it gives me weaker guarantees than atomic broadcasts with respect to order. And in order to do that, I'm going to use something that's called generic broadcast. Generic broadcast is kind of similar to atomic broadcast in that it also has agreement in total order, but the way in which order is defined is different. So generic broadcast uses a conflict relation, right? In this conflict relation, it tells me which messages must be ordered with respect to each other. So atomic broadcast orders all messages, right? Total order is given for all messages, but I don't have to do that. I may also be able to build a system by only ordering some of the messages, not all of the messages. Agreement is the same. If all servers deliver M or then either all servers deliver M or no server delivers M. Right? I don't want a situation where one server delivers it and other servers don't. But total order now says the following. Actually, it's not even total order. If methods M and M prime in conflict, right, according to my conflict relation, which I will define later, then I want all the servers to deliver them in the same order. But if they do not conflict, then I don't care about the order. I allow some methods to be delivered in different orders. So why do we do this? Well, we do this because So in reality, implementing atomic broadcast is an expensive atomic broadcast is an expensive property, an expensive communication primitive, because of the order requirement. So implementing total order is expensive, and since the applications not always need this total order, it may be more efficient to only provide it when it's really necessary. That's the motivation. So actually, atomic broadcast is a special case of generic broadcast. Orders everything. So every message conflicts with every other message. But if you are using this to build the deferred update replication mechanism, not all methods necessarily conflict. Because I think the easy way to think about this is, if two transactions, they use completely separate parts of the databases, why should I order them? Right? There is no need to order them. I can deliver them out of order. And the users are still going to see a consistent system. And it's going to be more efficient. So that's why it's done. So here's the way it's going to be. I can illustrate the system. I have two transactions, T1 and T2. These transactions here, they do not conflict. So they can be delivered out of order. So here, some methods, so some servers are going to deliver T2 before T1, and some other servers are going to deliver T1 before T2. Right? Oh, but I have to be careful when I deliver methods out of order, because if one transaction can have an effect on the other, they must be delivered in the same order. But I can actually capture my order relationship by looking at the read sets and the write sets of my transactions. So what this thing here says is, two transactions, they conflict, right? M and M prime, they conflict if the transactions that they carry, so here I represent this, I'm saying that message M is carrying transaction T and message M prime is carrying transaction T prime. So these two messages, they conflict if the two transactions, they either read what the other wrote or they both write something common. So if there is some intersection between the two transactions, then I must ensure total order for these transactions. But if the two transactions, they do not read or write anything in common, they can be delivered out of order. So that's the motivation. So let's look at a particular case. So we do gain if we are doing update transactions. But replacing atomic broadcast by generic broadcast in the deferred update replication technique has a cost, right? And this cost, it is translated into the read-only transactions. Remember, read-only transactions, they could be executed locally only. So I submit a read-only transaction, is executed in one site, and the response is, so the commit is performed without communicating, without the servers communicating. Now, I have to revisit this if I replace my atomic broadcast by a generic broadcast. Let me show you an example. So here I have my three servers, right? And there are two variables in my database. This server here, this transaction here, the only thing it does, it changes the value of X. This transaction here, it changes the value of Y. They don't read anything, right? Do these transactions conflict? No, they change different variables, right? Different locations of the database. So I can deliver them out of order, right? And it turns out that server 1 committed transaction T1 before transaction T2, and server 3 committed T2 before T1, out of order. Okay? Now let's assume that we had so that's the final state of the database after the two transactions are committed. Now let's assume that two transactions, T3 and T4, right, they are read-only, and they happen to read the values of X and the values of Y. These two transactions. But they execute at different servers. And as I said before, so we would like to execute read-only transactions completely locally, right? And then it happens that T3 executed at server 1 and T4 executed at server 3. So what's the state of the database that T3 is going to see when it reads X and Y? So it's going to see, when it reads X, it's going to see the change made by T1, right? It's going to see X equal to 1. But when it reads Y, it doesn't see transaction T2 yet, because it's delivered afterwards. So it sees the value of 0. So it's going to see X1 and Y0. Now what happens to transaction T4? When it reads X, it sees the original value of X, 0. And when it reads Y, it sees the change made by the second transaction. So in reality, I have a situation like this, right? Is this serializable? there is no way it can be serializable, right? There is no way I can place all these transactions in the same line so that all these 4 transactions can see these values. Well, why? Because for transaction T3, T1 happens before T2, right? And for transaction T4, T2 happens before T1. So there's no way I can swap my operations and my transactions and place them over a single line so that I can have, so that this execution is going to be equivalent to my concurrent execution. So what's the limitation here? I cannot have read-only transactions executing purely locally, right? If I replace my atomic broadcast by a generic broadcast. So there's going to be a cost in terms of my read-only transactions. How can I solve this? Well, I can give you two solutions. One is optimistic. So what I do basically is I have to handle read-only transactions just like any other transaction. I have to validate them. After the execution, I broadcast my transactions, and they're going to be ordered according to the generic broadcast ordering. And maybe some read-only transactions are going to be aborted, right? That's the cost. Now, another way to do this is a pessimistic solution. If transactions can pre-declare the items they read, right? If they know what they're going to read in the future, in some transactions you can do that, in some others you cannot do it. Then what you can do is you can broadcast the transaction before you start executing them. Why this works? Because generic broadcast takes care of the ordering and makes sure that I place my transactions in the right position, so they're going to read consistent information. But I must be able, so they never abort, right? Because I order them before I execute them. So in the first case, I first execute and then I broadcast. So I may actually, if the transaction reads inconsistent data, it's going to be aborted. In the second case, I first broadcast and then I execute. But in order to be able to do this, I must be able to pre-declare the data items that are going to be read by the transaction. So there is the costs of replacing total order by a partial order shows up in read-only transactions. Okay, and that actually brings me to the end of this talk. So what I try to do was to compare object and database replication, right? And we looked at 3 different aspects of it. First, their goals. And I told you that object replication was introduced for fault tolerance, while database replication was introduced for fault tolerance and performance. We had a look at different consistency models, and we saw that we saw 2 consistency models for objects, linearizability and sequential consistency, and you saw one for database, serializability. And then you looked at different algorithms. Primary backup and active replication, plus multi-primary passive replication for objects, and the deferred update replication for databases. So you saw that the different consistency criteria and the different goals, they lead to different algorithms. But it's not that these are completely different worlds. Actually, there are ways to bridge the difference between the 2 classes of algorithms. So we also saw the relationship between the consistent criteria, right? And I showed you how to reason about these algorithms using a common framework that hopefully simplifies the understanding of these many algorithms that exist. And then using these ideas, I showed you a new protocol, which is multi-primary passive replication. So most of the protocols that I showed you, they are based on group communication, right? Atomic broadcast, generic broadcast. So it turns out that this is so you can, by using group communication to design replication protocols, you can simplify the reasoning about the correctness of these systems, and you can also the solution become more modular because you don't have to actually consider how methods are going to be ordered, because atomic broadcast gives you this powerful and clean total order property. It turns out that I also have fewer aborts than atomic commitment. I didn't go into. There are also algorithms that allow you to terminate transactions using atomic commitment instead, which does not give you any ordering guarantees. And then, so there is, I guess, 15 years of research of replication using group communication, and it has been a quite happy union in both sides. So, in the one side, group communication, as I said, has helped database replication. On the other hand, research on the database replication has motivated more powerful and efficient group communication primitives, like generic broadcast, which was actually created, inspired by the way atomic broadcast was used to guarantee the correctness of databases. And other primitives which I didn't talk about, like optimistic primitives. So what I told you about was part of, actually it was mainly one chapter of a book that I recently edited with a number of people, and a little bit more of these two books here. So I had a preprint of the chapter 11, which I'm going to send to Sasha. So if you guys are interested in knowing more about what I talked about, I guess that would be the place to look at. And I also plan to make these slides available to, as you guys have a website where you put all these slides of your previous talks. So I open to questions if you want to ask them in public, or if you prefer to talk after the talk.